Hello everyone and welcome back again to the linear algebra component of the Calculus and Linear Algebra series. In the last video we introduced this idea of how to add, subtract and do the scalar multiplication of vectors in R2. And what we want to do now is we want to generalize this notion of vectors in R2 to some idea of vectors in Rn, as well as addition and multiplication and subtraction of vectors in Rn. And we're going to do that by, instead of constructing vectors now from ordered two tuples, we want to construct vectors, or at least their coordinate representations, from the set of ordered n tuples. Now we already noticed that it's rather tricky to think about these things in this geometric picture, because whereas before for vectors in R2 we could translate this idea of this coordinate representation into vectors, into kind of arrows in the two-dimensional plane, but if we're thinking of it now as n many coordinates, that would have to correspond to some arrow in an n-dimensional space, and generally it's not that easy to think about things in dimensions greater than 3 because we only have 3 spatial dimensions in our universe to think with. So let's go to our tablet and actually analyze the definition of what we might think of as vectors in Rn. So I've written our title here, and we want to kind of create a definition for what we mean by vectors in Rn. What does it mean by a vector in Rn? So the vectors in Rn are defined as the collection of ordered n tuples. These n tuples are what we construct from n many Cartesian products of the real numbers. So then, what does that mean? That a vector v in Rn then takes the form so we can write it in two ways. We can write it in this column vector form that we've talked about, or our row vector form. So we have v we write it as v1, comma v2, comma dot 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 up to vn, because there's n many components now because we've got n many copies of R. Alternatively, we can write it as v is in this column vector form, v1, v2, dot 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 up to vn. So as I say, these are just two different notations for the same idea. This is our column vector notation and our row vector notation. For now, though, I'll probably stick to the row vector notation for most of the stuff in this lecture. Okay, so I've already pointed out here that it's not so easy. We've already kind of, when I talked about moving from this computer science perspective of things as vectors as arrays, like we're kind of constructing it here, it's not so easy to move back to this visual or physics perspective given this amount of data, because now how can I kind of put n many points into only a three-dimensional space? I've not got enough dimensions to put all my information into. So I can't really visualize this thing so much as an arrow, or I can't picture this as an arrow somehow. I could equally define it as some sort of directed line segment in some higher dimensional space, but thinking in higher dimensions is rather tricky, so like we won't do that too much. It's better to think of it in terms of these arrays and the algebraic properties of those arrays. So much like how we defined addition in R2, where we added up the individual components, we can define addition in Rn by just adding up the individual components, because each component here is still a copy of the real numbers, and we know how to add two copies of the real numbers. So that leads us to our kind of extended definition. Now we want to talk about how we can add elements of Rn. So if we define, now we've got two vectors, but these two vectors now are in Rn, so they are of the form, we've got u is u1, comma u2 all the way up to un, and v is v1, comma v2 all the way up to vn. Then the vector addition of u and v, strictly speaking, this is the vector of addition in Rn. So I'll let u be the vector addition of u and v is given by the sum of the individual components, as you might expect. So we write u plus v. Again, this plus is different to the plus we're going to write in a minute. Is going to equal u1 plus v1, comma u2 plus v2, comma dot dot dot, comma un plus vn. So, in other words, again, this addition here is different. This is the addition between two vectors. And this addition is just the usual addition that we have between two real numbers, which we can define each of these pairs are real numbers, and therefore we can add them. So this is a reasonable definition of addition. If I perform this addition, each of these is going to result in a new real number, and therefore it's just going to result in a new vector, as per our definition of vectors in Rm. And equally speaking, as you might expect, we can also just extend simply our definition of scalar multiplication to Rn. So we could then take, let u say equal our vector u1 up to un, and c is our scalar now in R. Then the scalar multiplication of u and c is given by just extending it, the same one that we had for R2. We get c times u is going to equal, and then we just multiply using the usual multiplication of real numbers. That's just going to be c times u1, which is a new real number, c times u2 going up to c times un. And we see that's a perfectly valid definition. Here we've got c acts on u, should map it to a new vector. In other words, each of these terms here gives a new real number, and therefore this whole thing is some new vector in Rn. So this is a perfectly valid definition of scalar multiplication in Rm. And finally, it makes sense as well to define a reasonable notion of the zero vector in Rn. So whereas the zero vector in R2 was just in the coordinate form was just coordinate 0, 0, the zero vector in Rn is just going to be a coordinate form vector with n many zeros. So we could construct our definition of a zero vector in Rn. So we can say the zero vector again, we denote it by 0 with an underline here in Rn as opposed to R2 is defined as what? Well, we just define it as 0 is equal to 0, 0, n many times. So that is, we're saying here there's n many zeros. Okay, and using all these definitions, what we can actually do now is we can start to construct a kind of general theorem, or can kind of construct all the properties of additions and multiplication, scalar multiplications of vectors and zero vectors in Rn. And we end up with quite a long theorem here with all sorts of properties, and I'll write that out in detail. And this is in fact going to motivate much of the general abstract definitions when we move on to abstract vector spaces. So let's start with, we've got our theorem. And we're going to start off by just taking three general vectors. We've got let v, u, and w be vectors in Rn, so as per our definition before. And we'll take two scalars, C and D, in R. Then we have a lot of different properties now. So let's start with our first one. So we have our first property. The first one is the one that we've already proven for R2, which makes a lot of sense, that we've got u plus v is equal to v plus u. In other words, that the addition operation in Rn is commutative. So we can maybe write this as commutative. Okay, what's the next one? Well, we could also look at a property that is kind of a slightly different version that we've got now as u plus v first, and then if we first do u plus v and then we add w, that's the same as first doing v plus w and then adding u. And this is what is known as associativity. This might seem fairly obvious, but not all algebraic structures necessarily satisfy this property. But it is a property, and therefore we write it down. The third one is one that, again, we've kind of already shown for R2, that we have that say u plus the 0 vector is strictly equal to u. Indeed, we can also show that the 0 vector plus u is equal to u, and that just follows from the commutative property property I. And equally, I should say that this associativity property you could also prove for R2 as well. Right? R2 is a kind of special case of the Rn case when n equals 2. So whatever properties are satisfied by Rn will also be satisfied by R2. Any of the ones we haven't proven, just substituting in n equals 2. Okay, so what's our next one? Our next one that we've written here is that if we take u and we add on to it minus u, that is necessarily equal to the 0 vector. Now that might seem fairly obvious again, but it's really important to know that these notions of addition are not the same as the notions of addition across the real numbers. And likewise, this 0 vector is not the same as 0 in the real numbers, which is why this thing requires a proof. So whilst this is kind of a property that's fairly clear, it still requires a proof because it's not the exact same thing as what we're doing for the real numbers. The next one we have is we have that c times u plus v is the same as c times u plus c times v. In other words, that it is a distributive property, that c distributes over u and v. So this is a property that's, again, easy to prove, relatively easy to prove using just the properties of addition and scalar multiplication on Rn. Continuing. We also have a kind of distributive property now for the addition of two scalar numbers. So if we take vi, or number 6, we have c plus d times u is going to be the same as c times u plus d times u. Continuing, another property we have is that c times, if we first do d times u and then times it by c, that's the same as first doing c times d, where this is the times in the real numbers, this is not the scalar multiplication, and then act it on u via scalar multiplication. And the final one, which we have, is kind of an identity operation via scalar multiplication, which say if we take the number 1 in the real numbers and we act it on u via scalar multiplication, that's equal to just u itself. Now there's lots of things to prove here. Many of these are actually fairly easy to prove and some are fairly obvious, but I'm not going to prove all of them because it'll just take a long time. I'll prove 1 and 2, and then you can prove the rest yourself as exercises at home. So let's write down our proof for number 1. Well, number 1 is effectively just showing the commutativity of the addition defined on Rn. So if we let u equal u1, u2, to un, and v equal v1, v2, to vm, then what do we find as u plus v? U plus v is equal to u1 plus v1, u2 plus v2, to un plus vn. Now, addition on the real numbers is commutative. Right? This addition is commutative on the real numbers. If I do two real numbers, a plus b, that's the same as b plus a. So in other words, this is equal to v1 plus u1, v2 plus u2, vn plus un, which in turn is just the same as v plus u, where we've now got plus as our addition between two vectors in Rn. Okay, so that's our first bit proven. That's kind of part I proven. What about the second one? The second one is to say if I first do u plus v, and then I do w, if I add w, that's the same as adding v plus w and then adding on u. So in order to prove that, we will just define a new vector. So for I, we just need an additional one, w, which will let equal w1, w2, comma dot 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 to wn. So our first thing was we had what? We had u plus, I think it was v plus w. Oh, actually, I think it was initially u plus v, so let's do it the same way it's written up there. So we do first do u plus v, and then we will do w. Now that's going to be written as, we can write that first as doing u1 plus v1 plus w1, comma u2 plus v2 plus w2, all the way up to un plus vn plus wn. Okay, well, we can use the fact that, in fact, the real numbers are associative. That is, if we first do with real numbers, if we do u1 plus v1 and then add on w1, that's the same as first doing v1 plus w1 and then adding on u1. So because of the properties of addition on the real numbers, where again, to reiterate, this addition is not the same as this addition, we can use the properties of addition in the real numbers to prove some properties about addition on vectors in Rm. So now we have that this is u1 plus v1 plus w1, comma u2 plus v2 plus w2, comma dot dot dot, comma un plus vn plus wn. And we can write that now simply as u plus v plus w, which is exactly what we wanted to prove. So that's our first two statements proven, and as I said, I'll leave you as an exercise to prove the remaining statements. They're fairly easy to show, just using the definitions of scalar multiplication and vector addition on Rn. So that's where we're going to conclude the video. And in the next video, what we're going to do is, given that we've now constructed this structure of addition and scalar multiplication of vectors on Rn, we'll talk about what it means to take a linear combination, or when our vectors, linear combinations of vectors in Rm. So once again, I remind you to read the notes after watching this video or beforehand, and attempt any problems in the module handbook pertaining to some of the topics that were discussed in this video. So thanks very much for watching, and I'll see you in the next video.